take a look here at some new stuff. One-to-one inverse functions. Now, the thing that you got to think about an inverse function is just simply undoes what something else did. Fahrenheit to Celsius. So an inverse function will change Celsius into Fahrenheit. That's all that is. All it is. Don't think of it any more complicated than that. Now, when it comes to an inverse function, if I take g of, f of g of x, it's equal to x, and I take g of f of x and it equals x, we call these inverse functions. So we would say that g is going to be f to the negative 1. Inverse. You've seen the word for that negative 1 as an exponent used to identify inverses in the past. So, just some notation that you need to keep in mind. So, let's see, where's it? Okay. One thing that you got to think of is it one-to-one? If I put one thing in, do I get one thing back? Okay. So if I put 1 into the domain, what comes out? According to what you see there on the screen. 2. If I put 2 in, what do I get back out? 1. Is this always the case for everything that you see there? If I put in 4, I get out 8. If I put in 8, I get out 4. Okay. So the original function brought it here. The other function, the inverse function, takes it back. Okay. Always has to happen. So now, this leads us to this idea of a one-to-one function. Now, we've talked about functions before. A function, you put something in and you get something out. You put the same thing in and you always get the same thing out. It's that whole Pop-Tart toaster thing. You put a Pop-Tart in, what do you get out? You put it into a toaster. You get a toasted Pop, right? It doesn't magically change into a piece of bread, does it? Or a steak. It's not quite the appropriate place to cook a steak, right? So, if I put one thing in, I get one thing out, and the one thing that I get out can only come from one thing that I put in. Big picture idea that you got to keep in your mind. So, is each one of these functions one-to-one? Now, this is where you have to be able to put something into. Look at a function, understand what its graph is going to look like. Understand that what happens if you put something in. What do I get out? So, if I have 3x to the 4th power, you got a basic idea of what this graph looks like in your head. What would you expect it to look like? Well, is it going to be like a parabola? Or some kind of weird S shape that goes from one, comes from the bottom and goes to the top? Which one? The what? The parabola. It's going to have a bowl shape. So, if I put one number in, will I always get one number out? So pick a number. Put it in there. What would you get out? If I'm going to be lazy about it, I'll put in a 1. 1 to the 4th power is 1. 1 times 3 is 3. Well, I always get 3 out if I put 1 in. The answer is yes. So I got a function to do that. But if I put 1 in, I get out 3. If I look, hey, what did I get out of this thing? 3. What must have I put into it? Is that always the case? Is there another possibility that I could put a number in, raise it to the fourth power, and get 3 out? About negative. If I put -1 to the fourth power in, I get 1. 1 times 3 is 3. So, this is not a one-to-one function. If I put a number in, I get an answer out. That answer only comes from this one thing. Okay? So, if I'm walking around with a toasted Pop-Tart, you know what I put into the toaster? Pop-Tart, right? That works. But this doesn't. When you sit here and play this mind game with it, think of positives, think of negatives, and think of zeros. Okay? Generally, positives and negatives are the good things to look at. Right? So let's take a look at B. This is the same thing. If I put in 1, 1 to the third power is 1. What's 1 minus 1? 0. So if I put in 1, will I always get 0 out? Yes, no, maybe so. What happens if I put in a -1 like I did over on A? If I put a -1, I put -1 into the third power, that's a -1. -1 minus 1 is -2. Completely different number, correct? So my question for you is, when I put in a 1, I got a 0. Is there any other way to get 0 out of that function by putting in a different number? Or is 1 the only number that I put in for x that will ever be 0? This function is 1-to-1. I put a number in, I get an answer. That answer only comes from one number that goes in. Big picture idea that you got to have in your mind when it comes to this idea of 1-to-1. Now, you've heard of the vertical line test, correct? Got a graph, draw a vertical line. If it hits it in more than one spot, it's not a function. Yes. Now, the horizontal line test identifies if the inverse is a function. Also, kind of if it gives it 1-to-1. Think of that parabola. If I draw a horizontal line through a parabola, it can hit it in 2 spots. Yes? So, that means that for that particular value, there's 2 different inputs that'll give it to you. It is a function, but the inverse is not a function. So, I want to do this by the horizontal line test now. So I'm going to take my calculator. It's wrong calculator. So this one. Okay, so I'm going to put in 3x to the 4th power. Graph it. Let's see. Take a screenshot, and I want this to be only. And I do a. Okay, so now my horizontal line. If I go and take this and drag it through here, how many places does it hit? It hits in 2 different places. I got one right here. I've got one right here. Is it possible for this to be a 1-to-1 function? And the answer is no. Let's say that What gives me the value up over here is the value of 1. I put 1 in, it gives me this number up here. I put in negative 1 here, and it gives me the same value. So where negative 1 comes, let's see, it would be 3 if I'm not mistaken. Sorry. So if I put in negative 1, I get out 3. If I put in 1, I get out 3. What value do I put in if I want a 3? And you got to give me the correct number, otherwise you fail the entire course. Who wants to take that one? Who wants to guarantee an A for the whole course if they give me the correct number that I'm thinking of? Who wants to take that challenge? It's not even a possible number here. So the question would have to be, what gives me 3? If you can give me the correct number that gives me 3, no, I'm sorry, you fail. It's 1. Positive 1, yes. Somebody else want to take that challenge? Yes. I want 1 value. Positive 1? I'm sorry, you fail. It's negative 1. I can't have 1? I can't have an answer. Why? Because it's both of them. 2 values give me the same thing. There is no way, except if you want to try Wolf-Phileas's little trick there and say plus minus 1. Smarty pants over there, I tell you, you've got me. No. Huh? Well, no, I'll give him a C for creative thought. But you see the problem with this? If there's 2 possibilities, it's not a one-to-one function. So now if I go back and I take a look at the graph that they give me here, they want us to do, leave that out of there, they want us x to the 3rd power minus 1. So if I graph that, I got that. Screenshot, let's see, here, and I go paste. Now I go and take a look at what happens with this one, and if I grab my line and I drag it through and I try and find, always helps if I move that to the front. Let's see, format, border, bring the front, there we go. So, is there any place that line hits it in more than one spot? No. And since we know that this graph keeps on going like this, there isn't a place above it or below it that's going to have that happen. So, if I take a look at the values that I put in here, if I put in 1, I got 0, so that's 1 comma 0. If I were to put in negative 1, that kind of brings me down here, then it looks like I end up with negative 1 gives me negative 2. Is there a value that I can plug in here that will give me another 0 or another negative 2? Can I come up with one? And the answer is no, I cannot. So, 1 to 1. I know, it seems like I'm beating a dead horse, doesn't it? But, it's an expression. So, this is what it is. It's not that bad of an idea. Now, inverse functions. We talked about that a little bit at the beginning, where f of g of x is equal to x, and g of f of x is equal to x. Now, for it to go and have an inverse, it must be able to be 1 to 1. So, if I take a look at A here, is x to the 3rd minus 1, does it have an inverse function? And the answer would be yes. It is 1 to 1. I put one thing in, and I get one thing out. Now, because we've seen that by the graphs before, Now I want to verify that this is going to be the case for this right here. So I could put these in and do the graph and look at them and see what they are. But the only possible way that I'm going to verify it is if I do f of g of x. So, or g of f of x. So this is going to be my, oh, that is my g of x. So I am going to do f of g of x. So that one is going to be f of third root of x plus 1. Okay? So far, so good, yes? Now that means that I am going to have whatever this is, which is third root of x plus 1. I got to raise that to the third power minus 1. So, if I take the third root of something and then raise it to the third power, do I go right back to where it started from? Do they undo each other? Yes, they do. So I end up with x plus 1 minus 1, so I just end up with plain old equal to x. Okay, that worked out well. Let's try the other way. G of f of x. So that's going to be g of, well, what's f of x? Well, that's going to be x cubed minus 1. Okay. So I got to put that into the f function, so that means that I am going to get the third root of what's x? Well, x is x cubed minus 1 plus 1. If I simplify what's on the inside, I end up with the third root of x cubed. So if I take something to the third power and then take the third root of it, do I end up right back where I started from? The answer is yes. So I just verified that these two are inverses of each other. That's all I got to do. So find the domain and range of each function. Okay. Now, here's where it gets a little on the trickier side. Okay. So it says the cube root of any real number decreased by 1 is a real number, so the domain of f is a set of all real numbers. Well, that makes sense. The cube root of any real number plus 1 is also a real number, so the domain of g is a set of all real numbers. What this means is that for these two functions here, all real numbers, there isn't anything I can't plug into. They're odd power, odd root. Will always work out. The one that is going to cause you difficulty is going to be when you have something to an even power, even root. Then you're going to have to be very careful about your domain and ranges. So, finding the inverse of a function, doesn't it sound like it's going to be disgustingly terrible to do? The answer is no. If I want the inverse, all I got to do is switch x and y. So, let's try this. I want to go through and I want to find the inverse of that. So, paste that down here. Okay. When we do this, we're going to make a little bit of a change here for it. And the change that we end up having to make for it is we're going to take it out of function notation. I am not going to write it as f of x. I am going to write this as y is equal to 2x minus 1 over 3. Okay? Now, I want the inverse. Switch x and y. So, switch x and y. That means that it's going to be x is equal to 2y minus 1 over 3. Can you solve for y? That's easy enough, right? Multiply this side by a 3, multiply this side by a 3, so now I have 3x is equal to 2y minus 1. Add 1, so now I am at 3x plus 1 is equal to 2y. Divide by 2, divide by 2. So I have 3x plus 1 over 2 is equal to y, or in other words, y is equal to 3x plus 1 2. Are these inverses of each other? That's the question. So, we're going to graph them. Let's see what we come up with here. So, bring this one out. So, okay. Y is equal to, now I'm going to tell you this, and I've mentioned it before. When you put in rational expressions like this, use parentheses to separate your numerator and your denominator. That way the calculator knows exactly what you're talking about. 2x minus 1, close it, divided by 3, and parentheses 3x plus 1, close it, divided by 2. Graph. So, okay, are these actually going to work? Well, it's like this. Let's say I put in 6. 6 gets me out 3.6. Oh, that's an ugly number. Gives me 3.66666. Let's see what happens if I put in 1. 1, 2. Ah. Okay. If I put in 2, it gives me 1. Okay. That's in the first equation. So y1, if I put a 2 in here, I get out a 1. If I go to the next equation and I put in a 1, what should it give me back out? A 2. Why? Because into this equation I put in a 2, and it got me out a 1. So if I go to the other equation and put a 1 in, I should get out a 2. Okay. 1-to-1 function. Now I'm going to show you something else on here. Learned to notice this little trick the other day when I was playing with this with the trig calc kids. Enter changes the way it goes. But if I use this one here with a little dot behind it, watch what it does. Have this one set as so. The line that I am drawing through this right now is the line of reflection. This is always going to be reflected across the diagonal line y is equal to x. So what I see over here will be reflected over here. Okay? What I see down here gets reflected over there. So it's just the line of reflection, one of the things that you gotta be aware of. So let's see, we did that, so that. That's just what I was talking about. The graphs of inverse function are symmetric to the line of y is equal to x. See these guys here? Got the diagonal line going through here. If I reflect this line across that, I get this, right? You see that. So, let's... Now what happens if I have... Now we talked about this earlier, that this horizontal line hits it in 2 spots. Therefore, it cannot be 1-to-1. Therefore, it cannot have an inverse function. However, if we restrict its domain, if we say, hey, I only want to look at it from 0 up to infinity, or from negative infinity to 0, I am able to go and stop it and say, hey, I can look at what's going on here, instead if we limit the domain. So, I have an inverse function here if I limit the domain, right? The blue line can only be hit in one spot. It reflects across this, so whatever coordinates here, I switch the x and y and I get on the other side. But notice which function that is. That's the square root function. So, if I take a positive number and I square it, then I take that number and take the square root of it. What do we always say that the square root is? If I ask you what the square root of 25 is, you would reply with if I ask you what the square root of 25 is, the reply is 5. Why not negative? Because you were taught that whenever you take the square root of a number, it's always going to be positive. This is the reason why it must be positive. Because the square root function is the inverse function of the square function. The square function does not have a one-to-one function, or is not a one-to-one function, because there are two possible values for input for each outcome. If I restrict it to the positive numbers, which is what we were told when you first ran across the square root, you weren't told that specifically. This is the reason why it works the way it does. So finally, once in your mathematical career you understand now why something was taught to you the way it was. So I'm going to let it go there.